Okay, hello to class. So today we're going to be talking about electric fields and how they kind of work with forces. So we described Coulomb's law of the electric force, or Fe, as K is equal to Q1 Q2 over R squared. Now we're going to define the electric field, and the electric field is going to be F is equal to QE. And so then what this does is we can rearrange this very quickly to get E is equal to F over Q. And so basically the electric field from one charge is just that charge itself. So then E is just going to be equal to K Q over R squared. So this is going to be due to one charge. So for this, we can describe the electric field of a negative charge as always pointing inwards, like this. It's going to pull positive charges towards it. And we can describe positive charges as having an outward field that will repel other positive charges. Now, the definition here is the field E is defined as the force that would be felt by a unit positive test charge. And so that's why the negative one pulls in while the positive one pulls out. Let's get these field lines all nice. So one thing that we talked about with forces is that we can superposition them, and that helped us out a lot in Physics 1, and we talked a little bit about that concept earlier last lecture. So now, if we go ahead and I'll give you the exact equation for that. And so the superposition of fields is just given by E, say total, or ET, is going to be equal to sigma of n equals 1 to infinity of EI. And so then these are going to be vectors because they are field vectors. And so very quickly, we're going to go over a simple one-dimensional example with finding the field. Now, I saw that this was a relevant question on at least a homework assignment last semester. They used a different, as you can say, a different way of assigning homework. They didn't use expert TA. They used like Pearson or something like that. And so let's do this example because I do think it's a relevant one, and I think it makes sense to talk about it here. Okay, so we're gonna draw this. Here's our axes, right? And we'll have a negative charge there. It's going to have negative 2q here, and then we'll just use q as like a benchmark, and then we'll have a positive charge. This is usually how charges are denoted in physics. You'll have red as positive and blue for negative, and so then this one will just have some charge q, and then the distance between these two here is going to be d, or lowercase d. And so since this is a one-dimensional example, we can instantly say that that EY is going to be equal to 0 because there won't be we're not concerned about that. But in this example, I believe we are trying to find the point at which this there is a 0 field here. So we are looking for where EX is also going to be equal to 0. Obviously, these guys radiate fields, in this direction here, but we're only going to be considering this in one dimension here just to make it a little bit easier. Because there will be other points out here. Actually, no, there won't, because this will be pulling a unit test positive charge in, and this one would be pushing it out. So there's not going to be any points out here that are going to be exactly 0. It'll only lie on the x-axis here. Okay, so what we're going to be doing is there's going to be 2 places where this field is going to be equal to 0, and so those 2 places are going to be, if since there's 2, we can rationalize that we're going to have to use the quadratic formula here somewhere. So why don't we start with EX? EX is going to be equal to E1, and let's just add these up, E2. And so here we're going to say that this is going to be 2 and this is going to be 1 here. And so the field from E1 here is just going to be equal to KQ x squared, and I'm just using x as the distance from this charge here from the origin. And then here we're going to have plus minus 2kq because of the magnitude of the charge, and minus is going to be from the fact that it's a negative charge. And then we're going to go ahead and we'll just divide this by the distance from this charge, and we're going to be taking this from the origin here. So in this case, we're going to have x plus d squared. And so what we can do now is we're trying to find where this is equal to 0, so we'll set it equal to 0. And then we'll start solving for what x is. And eventually it'll get us to a quadratic, but we can go through and solve that pretty easily here. Okay, so first thing we have to do is we have to make sure that we're going to take this over to the other side. So we're going to have kq here over x squared is going to be equal to 2kq over x plus d squared. And so then the kq's cancel, right? And so then we'll cross multiply the denominators out. And so then that'll give us here, we'll say that this is going to be x plus d squared. And then this will be equal to 2 x squared. And we just did that by taking the x squared to this side and the x plus d squared to that side. So now let's expand this out. And so then that's going to give us x squared plus 2dx. And then we're going to have plus d squared. Now we can do a couple things here. Why don't we subtract everything to this side? So this is going to be equal to 2x. And so then on this side we're going to have 0. So I'll move that over a little bit. So we have 0 is going to be equal to x squared minus 2dx minus d squared. And so then now we can go and use our quadratic formula. So then here we can say that x is going to be equal to, there's a 1 here, that's going to be our a squared, or our a. So then on the bottom of our quadratic formula, we're just going to have a 2. And then on the top, we're going to have a 2d, but this b term is supposed to be negative. And then we'll have a plus or minus square root of b squared. So this is going to be 4d. And then it's going to be minus 4ac. So minus 4a is going to be 1. So then that's just going to be a 4. And then c is going to be a negative d squared. Oh, and this is also squared. So then that's going to give us a 4d squared as well. But there's a negative here. We have to account for that. And so then the 2 negatives cancel and you get a positive. And so then this is going to give you 2d plus or minus 8d squared all over 2. And so now we can go ahead and we can factor out a 2 here. And so then this is going to be 2d, and we can also factor out a d there. So this is going to be 2d plus or minus 2d square root of 2 all over 2. So the 2's cancel. And so then we can say that x here is going to be, we can factor out a d. So we'll have 1 plus or minus the square root of 2. And then very easily we see that this is going to be our answer. So then when this is going to be a plus, you'll get approximately 2.4d. And if it's a minus, it'll be slightly in between. So we're going to have one about here and then one about here. Okay. First example done. Oh, and yep, this just tells me where the other one is. And so then the other one is going to be negative 0.04d. So these are your two answers on where the electric field here is going to be equal to 0. So this is a very pertinent question that comes up a ton in homework assignments and sometimes on tests. So it is important to know kind of how to do this in this process here, because this is a question that will probably come up. Okay, let's do a little bit of a review because I feel like some of this stuff is a little more challenging to understand. So I'm going to go over some other things today. Okay, so next up we're going to talk about a little bit about a charged rod. And so let's say a rod has a length L. And so this is L. And has a uniform charge density of lambda. And so lambda here is going to be our linear charge density. And so then this is going to have the units right here of coulombs per meters. And so now in this case we can say we're going to find how much charge the rod contains. And so in this example, you can see that if you do some dimensional analysis, if you just multiply L by lambda, that'll give you how much charge you'll get. You guys can't see that. Okay, let's move this down a little bit. Okay, so this has a length L, and it has a charge density lambda. This is coulombs per meters. So in order to get Q, we just have to multiply lambda by L. I'll make that a little prettier. So that's how we get Q here for a one-dimensional rod. And so we're assuming that this rod is skinny enough here so that this radius is very, very small, or less than 1. So this is our condition for it being very, very, very thin. Okay, so this is very easy to see. You just multiply the length by the charge density. And you can also work this problem in vice versa. You can say that lambda is equal to Q over L. So if you have some rod with some charge Q and some length L, and it's assumed to be uniform as the charge is distributed evenly across the rod, then you can define this quantity lambda. And so now let's talk about a rod of length L with a non-uniform charge density. So in order to do this, we have to do a slightly different process with an integral here. And so then we can say that Q here is going to be from length A to B, or you could put this as 0 to L, but that's assuming that your rod is positioned at your origin. So we go from A to B, integrating over dq, and so I'm just going to go ahead and do it like this. And so, but then we have to replace q with this quantity here in differential form. So now, since lambda is not uniform, lambda is now a function of x. And for whatever function of lambda that is, you'll just write that this is from a to b of lambda x, because we're replacing dq with this, times dx. And so then you would integrate over this function, and this is going to be for some function of x. So this is how you would tackle that kind of problem. That won't show up too often here, but on occasion it will still show up. So now let's do another problem with a rod here. Okay, so this time we're going to be finding the electric field at a certain point. So this is going to be our x-axis here, our positive x-axis, and so then we're going to have a rod here, and so we're going to be finding the field here. This is our rod, and this is a length L here, so that's how long it is. And so what we're going to be doing here is we are going to have to go ahead and try to find the electric field at this point. So in order to do this, we have a couple things that we have to say. Okay, so it has a negative charge here, and we can take out a tiny sliver of length dr, or dx if you want to make it a little more consistent with what we're doing here. So let's do dx then. And in this little sliver of the rod, it's going to contain an infinitesimal charge element dq. And so if lambda is equal to negative q over L in this situation, then dq here is going to be equal to lambda dx, like we did in the last problem. But in this case, lambda is going to be a constant, since it's going to be, we're going to do uniform. This is going to be uniformly distributed, this charge over this rod. So then we can say that, all right, if we take the differential form of our electric field here, we can say that this is going to be equal to k dq over r squared. And so then we can go ahead and we can replace our dq in our equation with lambda dx. So then that looks like this. And in this case, we'll just go ahead and, since it's a one-dimensional example, we'll go ahead and we'll replace r here in this equation with x, so we can find the electric field at this point away. Okay, so now in order to find the electric field here, we have to say that, all right, well, we'll have to say that E is equal to the integral of dE. And then in this case, we're going to have to say, we're going to integrate from 0, or from A to A plus L. And so that'll be able to give us our electric field at that point away. Okay, so if we were to just integrate from 0 to A, we would just find the total electric field. That wouldn't really yield much. But so now let's do this. K and lambda are constants here, and so they come out. And so then we'll have that this is going to be dx over x squared. And let's make that a little better. Okay. And so then very quickly we can integrate this with some of the rules that we learned last time. And so then this is going to give us k lambda -1 over r from A plus L or from A to A plus L. And so now we can start plugging things in. And so then this will yield K lambda out front, and then this will be negative 1 over R of A plus lambda, because we're just plugging that in. This is again supposed to be X, excuse me, minus 1 over A. And this is going to be a double negative here. And so then we can just flop this around, and then this is going to be equal to K lambda 1 over A minus 1 over A plus L. And so now if we go ahead and we can just, plug in some constants here, we can say that, hey, let's do A is equal to 0.5 meters, L is equal to 1 meter, and Q is equal to some charge, or we'll do the elementary charge, and K is going to be equal to 9 is equal to 9 times 10 to the 9th. And so you can just plug those values in, and you can get a very, very quick answer here. So now if we were going to go back and talk about if this charge density varied, you would get a different answer. So the integral would look very similar, but then you would have to bring L back into the equation here, and then the integral becomes a little more difficult depending on whether or not lambda depends on a trigonomic function or whether it depends on a polynomial function. So this problem can change up a little bit depending on what lambda would be inside of the integral. But in a case where that is given, it is still very possible. Okay, so last example for the day before we move on. We're going to be talking, or last topic, we're going to be talking about the field of a charged ring here. And so let me just draw this out. So we have a ring here, right? And the ring is going to be stuffed with some positive charges here. Okay, and so this ring here, we can define the origin at the center of the ring, and we'll have axes going out either way. This will be, say, the z-axis. I'll lower that just a tiny bit. Okay, I've drawn this a little too high on my board. Okay, so I'm going to draw it reversed, so it's going to be flipped downwards. But we'll be working with it like it's in the positive direction here. Okay, so this is going to be the radius of our ring, R. And so now if we are trying to find the electric field at a point outside the ring here, on the z-axis here, we'll have that this angle here is going to be equal to theta, and that this distance from the ring to this point here is going to be R. And then this distance from the center of the ring to the point is going to be z. Okay, so for one point that we have to talk about is that EY and EZ at any point on the z-axis is going to be 0. And this is because we have symmetry here. We have symmetry inside the ring. Circularly, it is uniform, or it's uniform in charge density, and so then that means that this here means that all these points are an equidistance away no matter where we define this. And for a given point, theta is going to be the same all around the ring, and R never changes, and Z will never change as well. So all these things are going to be constants, and so then our electric field in the X and Y dimensions here, can't really see the Y dimension here, but if we were to define these two as, say, X and y dimensions here, you wouldn't be able to tell the difference between the electric field because there is no difference. So now in this case, the total electric field at any point along the axis here, because we're only talking about the axis because we have symmetry there, is going to be the electric field EZ. Okay, so in order to find this, we have to do a couple things. So now in this case, in order to find EZ, we have to integrate dEZ. And so now we first have to find what EZ is. So in this case, we're going to have to talk about some trigonometry here. So now in this case, the cosine of theta for this problem, if we're going to be using some of our trigonomic functions here, is going to be equal to z over r, as r is going to be our opposite, or r is going to be our hypotenuse, and z is going to be our opposite, and then r would be our adjacent here, because that is the radius here of this triangle. So if I was to draw this out, we would have a triangle like this. This would be r, or this would be capital R, this would be little r, and this would be z. Okay, so now in this case, EZ is going to be reliant on this cosine of r, and so then this is going to be equal to the integral of k cosine theta dq all over r squared. So now in this case, we have to go ahead and we have to swap around some of these variables in order to integrate this. So we can see now that this dq here is going to be due to, we're gonna in order this. All right, this is going to be a different problem finding dq here, because in this case we're going to have to take d lambda, or we're going to have to take lambda, and we're going to have to integrate it from 0 to 2 pi to find the total charge of a charged ring. But so for this equation, we're gonna stick with some of the basics here. So this equation here is going to be non-reliant upon theta. So in this case now, we're going to have to do something like this. So once we integrate this, this will come out super easy. So this will be k cosine theta, but we know that k is going to be equal to z over r. And so then that's going to give us kqz over r cubed here. R cubed, not r squared. Okay, and so from our Pythagorean theorem, this is going to give us, so since this is little r here, and so we have to do this in terms of given quantities, because little r is this guy here, so we have to give it in terms of these two. And so in order to do that, we know that r squared is going to be similar to, say, c squared is equal to a squared plus b squared. So in order to get r squared, we have to take big R squared plus z squared. And so then this now transforms into k qz all over big R squared plus z squared to the 3/2 power. And so then this will be our answer. And so now integrating to find the total charge, different problem, we'll handle that later. This is not like qz, it is q, the charge of the ring, the total charge of the ring, times z, which is this distance here. This is not one term, these are two different terms. And I'll mark that by putting those little dots in there, make them a little bit bigger so you guys can see them. Okay, so this is one quantity here. I want to stress to everybody very quickly that this is not a fundamental equation, but rather a result given to us by going through this process. And we want to learn how to do the process like this instead of just memorizing the result. Because this problem solving here that we get is going to be much more valuable than actually going through and doing this, or just memorizing that result here. Okay, so now I don't think we'll be doing a problem for this video. I'll try to do maybe one problem a week, but I'll be going over some more example problems next time. Okay, have a good day.